Well, hello, everyone. Thank you so much for joining me today. My name is Charles, and today I would love to tell you more about our multi-cloud experience, building a multi-tenant container platforms on Kubernetes and Vault. A bit more about me. I work on the container platform team at Snowflake. About more than a year and a half ago, my team started to build and operate a cloud agnostic container platforms based on Kubernetes. And today's talk is mostly about our experience and lessons of doing so. I am excited about cloud native infrastructure as well as ecosystem. So I've been a contributor to several open source projects in this domain. Previously, I worked at Cruise, a self-driving car startup, and my job was to design and implement a hybrid cloud Kubernetes platform spanning GCP as well as on-premise infrastructure. And before that, I was working at Google on the Istio team, the infamous open source service mesh. You can learn more about me at my personal website as well as by scanning the QR code. I would like to begin my presentations by sharing with you the key takeaways of this talk. I want you to take this message with you before I dive into the stories and analysis behind them. And then I will explain what Snowflake is, what is the data cloud, and what is the implications for the Snowflake infrastructure. And then I'll give an overview of our container platforms, what are its current scales, what are some technologies that we use, and what are the applications that we run on this platform. And then I'll dive right into the cloud agnostic abstractions and explain to you how this strategy has enabled us to expand our support into the three major cloud providers so efficiently. And Pulumi has been a very important tool to unlock the project success. I will share examples of our experience of using Pulumi to provision cloud resources as well as managing vaults. And from this experience, I want to point you at some of the key characteristics or features that you should be looking for in your next provisioning tools. And lastly, I'll discuss some open questions with multi-cloud that my team is still actively working on. So, takeaways. Cloud agnostic abstractions prevents fragmentations and proliferation of identities, policies, and toolings, but it's not always possible. Proliferation right here means the fact that you have to use different accounts and different user account and service accounts to access comparable services on different cloud. And it's even harder to manage policies because the IAM boundaries and IAM policies are totally different concepts and different API objects. And the toolings that you use to access those cloud services or the client libraries are also different. So essentially, you have the problem of fragmentations where you're doing one thing for Azure and a totally different things for Amazon and another different kind of setup for GCP. And that's just not scalable. And how do you assign different identities in different clouds that belongs to this essentially the same principles and governing the policies around that identity association? That's a challenge. And cloud agnostic abstractions definitely help in this case, but we will also discuss what are the cases that such abstractions is not possible yet. Secondly, declarative infrastructure is insufficient to solve lifecycle management. Invest in a tool that allows orchestration. Lifecycle management right here refers to cluster version upgrades or stepping out additional clusters by some predefined configurations. Orchestration becomes a key right here when we're operating at a scale of hundreds of clusters. Invest in a provisioning tools that has the melting point that supports this complicated orchestration because your infrastructure might be integrated with application onboarding and deployments, as well as non-cloud native infrastructure. And thirdly, your infrastructure provisioner is either your metadata store or orchestrated by a metadata store. And this store must be queryable. We used to store this metadata within an internal wiki page, or this metadata is scattered around the readmes across our code base. Those are very hard to query and has been a #1 headache in terms of implementing orchestrations or automations on top of different sets of tools that provisions the infrastructure and apps. So make sure that your infrastructure provides the interface that allows them to be queryable and orchestrated, or you define this metadata within your provisioner itself that expose an API to make it queryable. So the Snowflake overview. Snowflake presents itself as the data cloud that sits on top of the three biggest public cloud providers. Regardless of where our customer data sits, Snowflake provides one uniform execution platforms that unlocks all the data-related functionalities, such as data engineering, data warehousing, and data sharing. And because the Snowflake products are multi-cloud by nature, so are our infrastructure. Like I alluded to earlier, our container platform has experienced tremendous growth in the recent months. Currently, we are running 110 Kubernetes clusters, and my team is still building a lot more because of the business need. All the clusters averaged about 3,000 nodes in total, and that's about 60,000 containers. Because the cluster auto-scales, those are the average numbers. We built the container platforms on top of the managed Kubernetes offerings to reduce operational overhead for the control plans, but we do a lot more customizations and also add-ons on the clusters to make them a container platforms that supports multi-tenancies. All the clusters are regional clusters or multi-AZs and is deployed around the world. The clusters are multi-tenant. We support many different teams at Snowflake for their applications. And many teams share the same clusters, and oftentimes many apps share the same node. Multi-tenancy has unlocked around $7 million savings in last year, and we expect a lot more savings this year. And our container platform is integrated with the legacy VM-based infrastructure. Snowflake was founded in 2012, and that's before Kubernetes was available. So many of the infrastructure are still VM-based. We have to integrate with the existing infrastructure to make sure there's network line of sight, there's private DNS resolution. We're able to deliver the platform of this scale and scope because of the cloud native abstractions. We put a lot of thoughts into the subsystems that we use to reduce the customizations that we had to make for each individual clouds. We use Okta to reduce the proliferation of identity. Every users are assigned one Okta identity and assigned to several group membership. Each namespace is granted access to exactly one group. And Okta, combined with Teleport, ensured that users will only use one Teleport CLI to access all the different clusters and VMs on all different clouds. One lessons we learned from this project is that we should try as much as possible to push up the policies into cloud native components, such as pushing up network policies and mesh external traffic policies, authorization policies, and routing rules, firewall rules, or OPA gatekeeper policies. To further enhance multi-tenancies, we developed in-house custom resource definitions that abstract away the provisioning of blob storage buckets and objects, as well as KMS services by different clouds, also for vault policies for different tenants. So each tenant running in the namespace will have a dedicated subpath on Vault that they can use as the secret engine to store any kinds of secrets that they see fit. And lastly, for logging and monitoring, we're relying on the core Snowflake offering by itself, kind of like dogfooding our own products, where we are streaming all the container logs to Snowflake using a product called Snowpipe. Snowflake allows us to essentially write SQL to query our logs. Like I mentioned before, Pulumi has been a great fit for my team to provision cloud resources because Pulumi enables automation toolings and hence rapid infra scaling. We use Pulumi microstacks or multi-stacks, where we divided up the provisioning of each cluster into 3 separate chunks: the network, compute, and SQL. And doing so drastically reduced Pulumi preview time, which is sort of similar to Terraform Plan. Pulumi also makes cross-stack referencing really easy, so all the dependencies among the stack can be properly captured. The Pulumi automation API is really powerful. There are at least 4 use cases that I've seen in our internal code leveraging this feature. I'll focus on covering the first 2, where we implemented Blue-green upgrades for Kubernetes node pools to minimize any kinds of disruptions as well as incidents during the upgrades. We also generate cloud-specific Kubernetes manifests from Pulumi outputs. And I'll explain why we decided to define Kubernetes manifests outside of Pulumi and how Pulumi still makes any kinds of custom toolings really easy. In addition to those two, we have implemented custom rollout strategies for Pulumi stacks, which is important because we have hundreds of clusters that we operate, and we want to do some kind of canary testing before we roll out this code changes to all the clusters. And lastly, we leverage Pulumi Operator, which is a sort of agent pool CI/CD solutions so that we don't have to manually apply hundreds of stacks. The Blue-green upgrades for node pools. Blue-green upgrades for node pools is very similar for Blue-green upgrades for, say, any services where you provision a new version of the backend service, and then after you validate it, the new service is healthy and ready, we redirect all the traffic to the new version of the server and retire the old version. The Blue-green upgrades for node pools allows fast revert, and there's no chance for stuck between different versions. The upgrade steps are creating new node pools, coordinate and drain the old pools, and delete the old node pools after workloads has been migrated to the new pools and are running healthily. The problems with implementing Blue-green upgrades is that manual upgrades on hundreds of clusters is just error-prone and doesn't scale, especially because we expect to build a lot more in the future. Moreover, we cannot rely on cloud providers' auto upgrade feature because we have a really special Istio ingress setup, which is prompted by the product requirements that we must preserve the client source IP in every IP packets, combined with the fact that Azure doesn't have a cloud-native load balancer, where the Azure load balancers is using the nodes as the backends instead of the pods. So the traffic has to be routed to the nodes, and then it's IP tabled to the ingress gateway pods. And we do value consistency across different clouds, and we do want to have a consistent architecture across cloud. And therefore, we arrived at the special architecture where we're running Istio ingress in a dedicated node pool that doesn't auto-scale, and we're running the Istio ingress gateway as a daemon set pods. This kind of setup requires special coordinations during Blue-green upgrades, because when the Istio ingress pods are shifted or migrated to new sets of nodes, the old Istio nodes are still the backends of the load balancer receiving client traffic. However, there's no more Istio ingress pods on that node to handle such client traffic. Essentially, that means the load balancer is routing the client traffic into a black hole, and that's some kind of downtime that we cannot tolerate. Therefore, for the Istio pool upgrade, we kind of have to deregister the backend nodes from the load balancer, and then coordinate and drain the Istio gateway pods over to the new pools. We are able to automate the entire Blue-green upgrade procedures using the Pulumi Automation API. We built some custom toolings around this API that allows us to edit and apply the Pulumi stacks according to the upgrade steps that I just described, and we proceed one step at a time with some pre and post condition checks in between the steps to make sure that the steps are healthy and executed correctly. And unlike other infrastructure as code systems, Pulumi requires no DSL. It exposes the full-fledged programming language abstractions directly to the user, which is so powerful when we're trying to integrate with additional custom toolings and orchestration systems. The bottom line is that declarative infrastructure is insufficient to solve lifecycle management. Invest in a tool that allows orchestration. And automation and orchestration are so important to sustain at the scale that we operate. Another tooling that we built around Pulumi is to solve the cloud-specific Kubernetes manifests issue. Our application users need to customize their Kubernetes manifests to be able to run on multiple clusters or clouds. The reason is that the container image hosts where the load balancer labels or the pod identity annotations are usually different across clouds. The problem is that we're managing Kubernetes manifests outside of Pulumi. The reason is mostly because most open source projects that we use only release an installation YAML, and it's non-trivial work to translate that to the Pulumi setup. And second, the cluster space almost always digress from infrastructure as code sets because of the dynamic nature of the cluster due to reasons like different controllers or a horizontal pod autoscale. And lastly, we run a multi-tenant platform where we want our users to self-manage their own Kubernetes manifests. We don't want to be the bottleneck where we have to approve every configuration changes related to applications, but we also don't want to grant all the users equivalent access to Pulumi and our configuration platforms. Given the fact that we're building the Kubernetes manifests outside of Pulumi, the cluster-specific values are still stored in Pulumi because the cloud resources and the cluster itself is provisioned by Pulumi. So we need to build a tool that allows us to generate those Kubernetes manifests customized given the cloud-specific values. And that's why we built Overlay Manager, a YAML rendering engine. The Overlay Manager will read the Pulumi stack outputs using the API and generating the overlays that feeds into Kustomize, which renders the final Kubernetes manifests that was applied by Argo CD. In the cloud native community, we also saw alternative solutions such as using the DSL. Doing so still needs the input data from front-end framework to manage the Kubernetes configuration, the infrastructure provisioning tool. Some of the examples of this DSL approach includes Isopod or Q. The bottom line is that your infrastructure provisioner is either your metadata store or orchestrated by a metadata store, where the store must be queryable. In addition to Kubernetes and cloud resources, we also use Pulumi to provision and manage Vault deployments. Vault, or HashiCorp Vault, is a critical piece in our secret as a service and also private PKI. We use Pulumi to initialize and configure Vault. For example, we use Vault to issue and rotate the issue and CA cert for Cert Manager, and Cert Manager will sign the TLS cert used to terminate our private HTTPS traffic. We also replicate status secrets across deployments and regions using Pulumi to orchestrate this. And lastly, we enabled the cloud provider secret engine so that clients or applications can obtain from Vault short-lived tokens to talk to cloud providers instead of having to store long-lived static tokens, which is less secure. The tenant onboarding is outside of Pulumi. Recall our platform is multi-tenant, so we implemented this Vault policy custom resource definition where the platform user can define this Vault policy so that they can bind a list of Vault paths to a specific Kubernetes service account, and their applications could just use such service account when interacting with the Vault that's deployed in the cluster. An example of such Vault policy is shown on the right-hand side. My team has made some progress with multi-cloud, but some open questions remain. For example, applications still have to be cloud aware. They need to use cloud-specific client libraries to interact with cloud services and requiring code changes for each cloud providers we want to support. For example, if the application needs to read a file from the blob storage bucket or write to a message queue or PubSub topic, pod identity that translates a Kubernetes service account into a cloud service account only solves the authorization and authentication problems. The CRDs that we described earlier only resolves the resource provisioning aspect. Hence, the interaction between the applications and the cloud providers remain cloud specific. Essentially, you have to write the same code many times, and once for each cloud providers. And secondly, cloud agnostic abstractions often terminates at Kubernetes. Cloud resources and policies that cannot be pushed up remains heterogeneous across clouds. One example is when we use Cert Manager and Acme protocols to automatically renew our cluster public certificates that terminates the public HTTPS traffic. In order to solve the Acme DNS01 challenge, we have to make some DNS text record. So we want to reduce the cloud DNS permissions for Cert Manager to only making text records. However, we could not do so on GCP at least, because there's no record level permission control. And the IAM boundary is the entire GCP project. So essentially, we have to configure the permissions and security boundary controls per cloud. And this is the end of my talk. Thank you so much for being with me for the past 20 minutes. And if you are also excited about multi-cloud and distributed systems, container platforms, and open source software, my team is hiring aggressively. And please scan the QR code on the left and get in touch with us. Thank you so much.